Welcome back. Beside the issue with data formats and types, there are the situations that created inconsistencies in the mining results. One of them is the difference of magnitude among variables scales. Suppose we have three records described by two variables, color and position. The first record is red and has a defiant position. The second is red again, but shows a relaxed one. The third is green and has the same defiant position as the first one. Which pair of records is the most similar one? The red ones have the same color but distinct positions, while the red on the left and the green one share the same position. The thing is, usually similarity or distance measures weight the variables equally, and so we are not able to choose among those pairs. Now suppose that instead of color and position, we have age and annual income. This time the ones on the left share income, and the first and last ones have the same age. So again, they only differ in one variable. And now, which pair of records is the most similar one? Is it now possible to choose? It is indeed. The red ones are the most similar ones. For example, if we apply the Euclidean distance as usual, the difference between both pairs is completely different. The distance between the red ones is 25, and the distance between each red one and the green is approximately 1000. So the green one has no chance to be most similar to the first record. But if we look closely at the example, we are able to see that the red ones have double the age of one another, and they both have around 97% of the income of the green one. So, common sense would choose the first red and green records as the most similar ones, since they share the same age and their income is not too different. The solution to this problem is to scale all variables to the same range through a scaling technique. Most of all, there are essentially two techniques to do it: normalization and standardization. The normalization maps the values assigned to a variable to a new chosen range. The new minimum and maximum values are then applied to map all the variables describing the dataset. In this manner, each value is just transformed into a new one, preserving the relationships among the original known values. However, if we encounter a higher or lower variable than the known ones in the future, we will face an out-of-bounds error. The most usual range chosen is the one between 0 and 1, giving a very perceptive understanding of the data. Consider our iris dataset again. The box plot shows the ranges for the four variables describing the flowers, and despite there is no very strong difference among those ranges, they can be normalized into a new range, eliminating any undesired excessive relevance. So, in order to transform to the range between 0 and 1, we would have to apply the given formula to each value for each variable. For example, the first record with a sepal length of 5.9 would become 0.44, given that the minimum and maximum for the sepal length variable are 4.3 and 7.9 respectively, as we can see on the table on the right. After applying this transformation to all values assigned to each one of the variables, we would have a different box plot for our dataset. Here, it is clear that from now on, no variable will have a higher weight than the others. Note that the data distribution does not change, but that the standard deviation value can be profoundly changed. In this context, outliers are treated as regular points, contained in the same range as the rest of the values. But in order to accommodate outliers, the rest of the data is naturally concentrated around the mean value. In the case where we reduce the range of the data to be considered, for example between 0 and 1, we may significantly reduce the range for the regular values, which can make it more difficult to distinguish between them. The second choice is standardization, and computes a transformation based on the mean value and standard deviation of each variable. So, Each original value becomes its distance to the mean value of the variable divided by its standard deviation. In some way, it is a measure of how many standard deviations the value deviates from the mean of the population. With this transformation, values become negative if below the mean and positive if above it. This score has the advantage of not requiring to choose any boundaries in advance, which avoids any error in the presence of unseen values. Following the example above, 5.9 in the sepal length would become 0.07, since its mean value was 5.84 and its standard deviation was 0.83, as is shown in the 5 measures summary. After applying the transformation to all values assigned to each one of the variables, we reach a different box plot for our datasets, with all the data around zero. Without establishing previous limits, this type of transformation is more robust to the existence of outliers, and therefore preferable in the presence of a large number of these cases. This kind of transformation is really important when distance-based mining techniques are to be used, which is the case of a large number of classification and clustering methods. Another example where this is relevant is the case of the majority of training algorithms for neural networks and other methods that weight each variable, since again the different magnitudes make it more difficult to adjust the weights. Next, we will be addressing one last transformation: balancing datasets. Bye-bye!